Good afternoon, everyone. We are Johan, Steen and Sjouke Vandenberghe. We are PhD students in statistics. And our group develops statistical methods for inferring cause-effect relations from data. In this talk, we will talk about mediation analysis, and we will illustrate this using a specific smoking example. About 8 years ago, a study published in Nature reported an association between a genetic variant on chromosome 15 and lung cancer. In that same year, another study reported that this same genetic variant was also related to smoking intensity and nicotine dependence. Given the known fact that smoking causes lung cancer, these combined findings left researchers with the question whether the effect of this genetic variant on lung cancer could be explained by its effect on smoking intensity. Questions about such causal mechanisms, such as this one, are very common across all fields of empirical research, and they can be answered via mediation analysis. Mediation analysis is a statistical technique that aims to disentangle the effect of a certain exposure, such as the presence of a genetic variant on an outcome such as lung cancer, into an indirect effect via a certain intermediate variable or mediator, such as smoking status, and the remaining direct effect through possible other mechanisms. In this talk, we will give you a flavor of some of the issues, illustrating this with this smoking example. Now consider in particular the relationship between smoking and lung cancer. Although observational studies in the 1950s found high correlations between smoking and lung cancer, this in itself is not enough to serve as evidence of a causal effect. Why is that? Because smokers and non-smokers are very different, not only in their smoking behavior, but also in many other aspects. For instance, factory workers in that time were more likely to smoke, and they were also more likely to develop lung cancer because of asbestos exposure. Such common causes may distort the relationship between smoking and lung cancer. Now, the following example might make it more clear why association and causation are often not the same. Consider an observational study where we just observe who smokes and who doesn't, and who gets lung cancer and who doesn't. Then in this study, we can now compare the risk of getting lung cancer in people who smoke, which is 2 out of 4, and the risk of getting lung cancer in people that don't smoke, which is 0. So on average, the risk of getting lung cancer is higher in the smoking group than in the non-smoking group. However, to infer a causal effect, we would like to have comparable groups that only differ in their smoking behavior, as we would get from a randomized experiment. So in causal inference, we imagine what would happen. We imagine what would happen if everyone smoked versus if no one smoked. Although we can evidently not see from our data at hand whether people who smoke would potentially also get lung cancer if they didn't smoke, there are recent statistical developments in causal inference that are able to make such comparisons under minimal and well-understood assumptions.
Okay, so let us now return to our mediation example. Routine methods in mediation analysis are typically based on fitting a set of regression models, such as the ones displayed here, and then combining parameters from these models. So an immensely popular approach in social sciences is to compute the indirect effects as the product of the effect of the genetic variant on smoking, as captured by parameter alpha-1, times the effect of smoking on cancer captured by beta-2. Unfortunately, products of regression coefficients have no meaningful interpretation and in general, and therefore these methods are essentially useless. So in our work and that of others, we therefore investigate specifically how one may define direct and indirect effects. The potential outcomes framework introduced by Sjouke in the previous slides has been very helpful in that respect. So consider again our population of interest. Some people are carriers of the genetic variant, whereas others are non-carriers. Let's focus on the carriers and try again to imagine a hypothetical situation in which everyone would be carriers. Under this scenario, it's very likely that non-carriers have a different smoking status and lung cancer risk than what we actually observe. However, in reality, we do not observe these potential outcomes. Let us now again consider the same scenario where everyone is a carrier, but now try to imagine whether they would develop lung cancer if we were to change their smoking behavior as if it would be if they were non-carrier. So this associated change in the risk of lung cancer formalizes the notion of an indirect effect. So to what extent would the risk of lung cancer change if we were to change their smoking behavior, everyone's smoking behavior, from what it would be if they were carrier to what it would be if they were non-carrier. So Robbins and Greenland and Judea Pearl have come up with these notions and have also developed strategies for calculating these effects. So this approach has been recently used by a group of researchers using combined data from different studies. Their meta-analysis pointed out that only 3 to 5% of the effect of the genetic variant was mediated by smoking intensity. However, it already also indicated that the direct effect of the genetic variant differed between smokers and non-smokers. In fact, for non-smokers, this link was practically non-existent, whereas for smokers, the direct effect increased with increasing smoking intensity, confirming this news item from several years ago. Note that traditional methods would not have been able to pick this subtle finding. So in our research, we work along these lines to develop mediation analysis techniques for more challenging problems motivated by specific case studies. In the last part of this presentation, we would therefore like to give a short outline of our research focus. In most applications, one can imagine multiple causal mechanisms to be at play rather than a single mechanism. In recent work, we have therefore attempted to generalize definitions beyond single mediator settings. However, this has turned out not to be such a trivial task, especially when mediators affect one another, as is mostly the case in realistic applications. A first complication that we face is that our framework conceptualizes changing the exposure on some pathway but not on others. So as the number of mediators increases, the number of ways in which we can change the exposure on some pathway and not others increases exponentially. To overcome such a curse of dimensionality problem, we develop statistical methods that are specifically tailored towards mediation analysis. We have already mentioned that to infer cause-effect relationships, it's important to adjust for common causes. However, this becomes much more complicated in mediation analysis because then common causes of smoking and cancer, such as, for instance, alcohol consumption, may themselves be affected by genetic factors. So, in other words, common causes may be mediators at the same time. How to best account for this is a big open problem in mediation analysis, which we are currently developing solutions for. A further challenge is that the risk of incorrect modeling assumptions increases as more and more common causes and mediators enter the picture. To prevent bias, we therefore develop methods that are less sensitive to model misspecification and that can flexibly be used when dealing with a mix of continuous and discrete data. Natural effect models for potential outcomes, for instance, allow for much more flexible modeling and also yield results that are easier to interpret and to report. These models can be fitted for single mediator settings using our homemade software package Medflex for R. So because of time constraints, I'll skip this part. So as a take-home message, we can say that mediation analysis has been completely reassessed within the framework of potential outcomes, which has brought us a formal language for providing clear definitions, explicit assumptions, and flexible modeling approaches. Thanks for your attention.
Questions? Yes, please.
Medflex.